Good morning, everyone. Can you hear me? Is my audio coming across? Good. Yesterday, I had a little glitch with my audio. I checked the audio box before you enter a session, and it was weird. The technology is great, but sometimes we lose out, but that's okay. Now, what I want to do today is continue what we have been doing in our lecture. Um, we've talked about area bounded by curves, and we've talked about some methods having to do with the disk method and the washer method. And what I want to do today is do some more examples of that and then talk about a shell method and then come back to the cross-section method later, just so that we can make sure that we have these methods down. The cross-section method is very different from the shell method and the disk method. So I want to go ahead and talk about the shell method first. Now, let me go ahead and share my screen. The first example will be this one. That is, it says use the disk method to derive a formula for the volume of a sphere of radius r greater than 0. So when we think of a sphere, we think of it having a constant radius. So this is constant. So now when you think about doing a problem like this and the instructions say use a disk method, you think about revolving a particular region about an axis. And so what I've done here, and I want you to think about this, I want you to visualize this. This says, as a hint, and of course there are many ways to do this problem, but you can use this particular curve. That is y equals the square root of r squared minus x squared for some positive constant. And if you look at this, this is just a semicircle. This is the upper arc of a circle of radius r centered at the origin. So think about this for a few seconds and then we'll discuss it. Again, if you like, draw a sketch of the semicircle and think of how you could actually impose a rectangle that you can revolve. That is, think disk method. So what I wanted to do is just kind of have a little reveal with this one. Notice what we've done here in this particular case is I've drawn a semicircle here. Now, when you think about the semicircle, the actual values of x run from negative r to r. And in this particular case, if we revolve this region, and I'll shade in this region, about the x-axis, upon doing that revolution, we would form a solid of revolution, and that is a sphere. So again, notice the hint was the disk method because in this particular case, the actual rectangle touches the axis of revolution throughout the region. Again, this makes a very simple application of the disk method that provides another connection to geometry, which I talked about in the last lecture. So now what we can do, and this evolves very quickly and very easily. I always like to use symmetry because if the symmetry is present, then it can usually make the computation a little bit easier. So see if you agree with me. Now, when we look at this, we can take X to live between 0 and R. And notice that on either side of the y-axis, we have a symmetric region. So the disk method would serve us well if we just integrate in this region and then multiply the result by 2. Now, of course, you don't have to use this, but we always, in general, like a lower limit of 0, because that usually means a simpler time applying the fundamental theorem of calculus. So again, when you think about these equations, let me go right back up here and make a notation here. We have x squared plus y squared equals r squared. Again, that's just the standard equation for a circle of radius r centered at the origin. And all I did here was just to solve for the y. Again, you know how to do this, but the circular functions and the conic sections often get rusty. And then, of course, we can apply the square root principle, plus or minus the square root of r squared minus x squared. Now, in this particular problem, you're thinking, well, how did I come up with this curve and why did I make this hint? Well, now we see if we just select the positive square root, we have the upper arc here. And so now when we select an x between 0 and r, we can simply draw the rectangle, and then we know that the length of the rectangle will just be given by the function formula. So if we've chosen the positive square root here, we can select the radius function to just be the square root of r squared minus x squared. So the circular functions are very, very useful in calculus. And when you get to calculus 3, you'll see that more and more. We tend to manipulate what geometry we know to solve as many problems as we can. And physicists do the same thing, especially when you study electricity and magnetism. These types of results will be very, very useful. That's why you learn your calculus before you take physics, because physics relies on the language of mathematics. So now what we can do is recall, remember, if we have volume, I'll go ahead and write this in. Volume now will be pi, and whatever our limits of integration are, a to b, say in general. And then, of course, we have r, I'll use this superscript notation, the radius squared dx. So that's just a simple rendering of the definition of this method. So if we apply this, remember, we have the symmetry factor of 2, then we have the pi, and then the limits of integration would just be from 0 to r. Now, of course, you can see why this method is really nice here, because the radius function is the square root of r squared minus x squared. And then, of course, using the area of the circle, we square this. And so upon squaring the radical, we are relieved of the radical. So we actually make this problem much simpler. What's interesting about these problems is that on occasion, you may find that when you start out, you've got radicals, you've got complicated integrands, and then upon doing the algebra, you end up with something simple like you have in calculus 1. So now here, we have now the integral 2 pi 0 to r of r squared minus x squared. Now this is where students tend to be a little less adept at doing these problems. Remember, when you're dealing with letters, you have to respect the letters, you have to respect the numbers. It's like doing symbolic computation doing mixture problems or time rate distance problems in pre-calc. If you don't do prime factorizations and treat the numbers with some type of allegiance, you get off path really fast. So now this is treated as a constant. So when we do the anti-differentiation, we just get r squared x. Very simple. Like if we have a 2, we get 2x. And then of course here we just add 1 and divide by the new power. So the antiderivative here is very straightforward. Now, of course, remember, we're going to integrate from 0 to r. Now, like I said in the past, usually I'm always going to try to do a warm-up when it makes sense. Sometimes we may not be in a place to do that. Now, of course, and this is what I said before, the lower limit now here is 0, and that annihilates the integrand. So we don't have to worry about that. So let's go ahead and substitute r for the x variable. Now here we have r squared times r, that gives us r cubed. And here we have r cubed divided by 3, which we have here. Now again, you're thinking the problems we did last time were very difficult in the sense that we had lots of fractions. This one is a relief. So now if you like, we can do a common denominator of 3. So we extract the 1/3, and then of course that will give us 3r cubed minus r cubed. And then of course subtracting, we have a 2r cubed. And then if we multiply the two copies of 2, we get 4 pi over 3 r cubed. And that is the standard formula for the volume of a sphere of radius r. So again, what we're seeing, and as you know very well, when you took your high school geometry class, all these formulas were provided to you. And then of course your teacher would do a maybe justification of some of the formulas that you could understand at the time. But what you can see here is when you start looking at curves in general, the actual derivations require infinitesimals. That is, they require the use of calculus. And the Greeks actually had their own method of calculus before it was even invented. And again, I don't think a society like that will ever exist again. They were really smart people. Maybe history will serve us well, and they'll think we're pretty smart because our generations came up with a lot of nice technology. Who knows how we'll be treated in history? But it's always good to hope that it will be a positive treatment. Okay, so now what we see is the disk method can provide certain derivations of geometric formulas that we've to this point taken for granted. Now, I promised last time that I would do a derivation, and this is the problem, and I'll work this out like we did the last one. In your WebAssign, you have an example that talks about determining a formula for the volume of a ring. Now, this is why I did the sphere first to get us warmed up, because this one's a little bit more complicated. So let me write this down. Here's an example. And then we'll start talking about the shell method. A manufacturer drills a hole through the center of a metal sphere. It'll certainly be able to speak. I think, like another month and a half of these Invisalign, and boy, it's hard to say sphere. So my students last semester would laugh at me because I would spit so much when I spoke, and I apologize for that, but my orthodontist would shoot me if he knew that I wasn't wearing these things. So again, this won't be too much longer. And we have a sphere of radius r. And you're probably saying too much information. Yeah, I just thought I'd add a little bit of humor. Now, the hole that's been drilled has radius r. These are all constants. And of course, r is less than uppercase R. So you're thinking here, we're going to have to use some kind of method that deals with an outer and inner radius. And we're already taking the letters that we normally use. And unfortunately, that happens in math. And then the direction is to find the volume of the resulting ring. Now, lots of times, as most of you all I know are either future computer science professionals, or a lot of you probably engineers. I've got a lot of students who want to be chemical engineers because they're interested in working at LyondellBasell or some similar huge manufacturer of all the chemicals that we need in society, or maybe mechanical engineers. And so this problem is something that would be of interest to you. So what I want to do is maybe set this up so that we can see what the technique would be. Because right now it's like the last problem was fairly straightforward. We know we've got circular functions working here, but how does this evolve into a method that we've already learned? So let's go ahead and draw a sphere. And we'll kind of use maybe our intuition to drill the hole and make it look believable. Good old whiteout. That's the best thing. Liquid paper is too long. This stuff is really nice. So we have this sphere, and now we're going to drill a hole through the center. And that's going to have a radius r. So we're just trying to see if we were thinking of a manufacturing process, what would the schematic be? Engineers have to come up with schematics and say, okay, well, I've thought about this. This is what you need to do. So we'll go ahead and mark this. Now, again, we're working with the center. So go ahead and eyeball the center and mark in the radius of the sphere, which is r. Now, what I'm going to do is impose some axes. So let's just impose a vertical axis and then a horizontal axis. Okay, now what I'm trying to do is show you that upon imposing these axes, it kind of gives us an idea of what we need to do. Now, notice this part here is removed. So if we think about the actual ring, this cross section here, again, I thought about this and I said, what's the easiest way to provide an explanation of this that my students will understand? In my honor sections, I would just give this as a project, but I teach the same things. I just teach them differently for my regular sections. So now you can see with this particular schematic if we actually revolve this shaded region about this axis here, that will generate the ring. And again, it's like, okay, I see what that is. You know, when you think about the process of drilling the hole through the center of the metal sphere, okay, boom, you can visualize it. But now mathematically, excuse me, we can see that we can now transform this to a washer method. Now, what's important here is it's not up here, it's here. So we're going to move this part over. We're going to rotate it and make the picture look a little bit easier. This is a little bit awkward, and we want to get the algebra correct. So now this will imply, let's go ahead and draw another picture here. And of course, we're going to try to use some symmetry because, you know, we want to make the process as simple as possible. So I'm going to impose axes here. Now notice, I'll go up R here. And then I'm just going to draw this part here and then chop it up. Again, just kind of eyeball these. Doesn't have to be a work of art. So now we have this arc right here. Now we're going to impose these distances. That is where we've drilled. So this is R, lowercase and uppercase there. So here we have that right there. And then this distance, this one here, right there. Now, let's go ahead and dot across here. And this shading now is this shading. So when you look at this problem, it's not trivial at all. But the sphere problem you could do probably figure out pretty quickly. But this does take a little bit more thought. And of course, that's what you find in your math classes as you progress. The problems get more difficult and the thought process is more complicated. Now, you're thinking, well, you know, Professor Ron, you're gonna think of using some symmetry because on either side of the y-axis we have the same region, and I'll think about that. So I really need to figure out what this point is. Now, just like we did before, this outer curve is y equals the square root. Again, now the radius is uppercase R, so we have uppercase R squared minus X squared. So that's just like with the sphere, but now we have this radius as opposed to the lowercase. And so now we just want to check ordinates. So we need to find these 2 points here. So now let's check ordinates. So set R, this R equal to this function and solve for X. So just very simple algebra. It's easy, but we just have to figure it out. You could probably guess, but don't do that. So now square both sides. And now we can transpose. We can take the X squared over to the left and the R squared over to the right, the lowercase, of course. And so now we're back to the square root property. You know, good old college algebra. It's probably one of the most difficult theorems for students to remember, but it is unique to real numbers. The real numbers are odd, but odd in a way that we can remember. So now X equals plus or minus the square root of uppercase R squared minus lowercase r squared. So now we can write these in. So what we can see here is now we're set up, but I'm going to be lazy. You can be lazy as long as it's correct. And we've got a 0 there. So what we're going to do is let x, just like we did for the sphere, live between 0 and the square root of r uppercase R squared minus lowercase r squared. Kind of hard to say, but that's what we've written. And then we will use symmetry. So we'll need a factor of 2. So again, this is a non-trivial problem that is important that you learn how to do because when we do these kinds of methods, if we're going to get any better, we have to kind of stretch a little. Now notice we will do, take your red pen and do that. That is, we want to revolve around the x-axis. Ricardo, do you have a question? I've got a little ask to unmute. Oh, I'm sorry. That's just where my pointer is. Sorry. This Zoom is fascinating, but I think it does have a mind of its own. Now, here, let me move this up here. This over here for now. So let's go ahead and get our outer radius and our inner. So here, for instance, we'll say, since I'm already using R, I'll say inner radius. Just pick an X, say right there. So inner radius. And then to here, outer radius. So you just take an X and then just go pick. So this implies, and I'll use outer since we're using the letters, outer radius equals, and that'll just be the function, square root R squared minus X squared. That's usually what we call the uppercase R, but we're already using those letters, so I'm not going to repeat them. And the inner radius is going to be fixed. It's always going to be lowercase r. So this is definitely, this equivalently is the washer method. So we know this is the washer method because we see here that the region that we're revolving does not touch the axis of revolution. So this is necessarily the washer method. It could touch it some places, but still that gives the washer method. So now let's go ahead and push everything through. We've got everything that we need. So this implies, and I may have to go onto another sheet, but I'll see if I can squeeze everything in. The volume. Now notice we're going to use the symmetry, integrate from 0 to the radical here. So first, and do this in another color, put the 2 here and just write symmetry. And then, of course, we have the pi. And then we integrate from 0 to the radical. I'll say the radicals because I'm referring to that. R squared uppercase minus R squared lowercase. And then we have our outer radius squared. I'll use a bracket here. Square that, minus the inner radius squared. Remember, the washer method is just 2 applications of the disk method. That's it. Very simple. So now we have 2 pi. We have the integral from 0 to the radical. And now, of course, when we square this, we're relieved. Oh, and sorry, that's an X. That would make for much of a problem. See, that's what's so good about the math. It just self-corrects. So we need the X squared there. So now when we square, we get R squared minus X squared minus R squared dx. Again, this is how I've noticed your homework looks good, your quizzes look good. It's kind of frustrating at times. I know, you need to type an exact answer, or if you have a typo. And just remember, as I look through your quizzes, I look for typos, I look for any kind of careless errors to give you credit. So don't worry about that. I'll always look over things, because sometimes WebAssign can be picky, and you can write an equivalent answer, which is fine. So don't worry that, I'll work through these and see and assign that partial credit so you get the credit you've earned. But like I say, as you work through everything, you're seeing that the WebAssign keeps you on track. It says, okay, you've got to write down exactly what you mean. And so we write down enough so we can go back and check everything. Now remember, these are both constants. So in your notes, take your red pen, constant. So now, again, you're thinking, well, these are the easiest integrals in the world, and they are, but it's not that that's difficult. It's the setup, even though this is just important. Remember, in pre-cal, you do the time, rate, distance. Every part is important. Every part is essential. So now we get 2 pi. So we have r squared x, uppercase, and now we have x squared, x cubed over 3, add 1, divide by the new power. And here we have a minus r squared x. Sometimes the simplest problems are the most difficult. We always want to rush to the punch line, to the finish line. So take your time. Now, when we see this, notice again, and I will say this a million times in this class when we have integrals, the 0 annihilates all of this integrand. So if you use the symmetry, you have less work. Don't use this if there is no symmetry, clearly, but when you have symmetry, this technique will make your work easier. So please try it out, see what you think. So now we have 2 pi. So now we substitute the radical in for x. So this is going to be r squared. And as we have this, let's just go ahead and write this with the 1/2 power. Be a little bit easy to see at first, then we'll change it out. Okay, and then we have minus, we have r squared little r squared there, and then minus r squared minus little r squared to the 3/2 over 3. Make sure you can see that 2 there. And then minus r squared times the radical. So the issue with this problem is just trying to keep all of the letters in check. So again, uppercase r squared times the radical. We take the radical and raise it to the 3rd power, so we get 3/2, division by 3. And then here we have lowercase r squared times the radical with the negative. Now, if you will, we don't like complications here. So notice we have a radical in everything. So let's go ahead and factor that. And if you like, we can go ahead and factor a 1/3. So we have 2 pi over 3, and then we have the radical. So now we just doing the due diligence like you do in a physics class to make your formulas look nice. So here we've removed the radical, but we've also removed the 3. So we need a 3r squared. Now, when we look here, we've removed the third and we've removed 1 radical, but we left the power 1 behind. So we have minus r squared minus little r squared. And then when we look to this term, we've removed the radical, but we didn't have the third. So we have minus 3r squared, lowercase. So what's interesting about this particular problem, and what I've noticed here when you do these types of problems, is that we're just using calculus 1 techniques. Now let's simplify this. We learned everything we needed to know about this class in Cal 1. I'm not teaching you a lot of new math. I'm just using the math you already know and recasting it. So we got just court reporter here. And so now we have 3r squared minus the r squared. So that gives us 2r squared. And here, ladies and gentlemen, we have a negative negative. So that's a positive r squared minus a 3r squared, which is a minus 2r squared lowercase. Okay, so again, just we're now court reporters. We're making sure that we're typing all of the litigation correctly so we can keep our jobs. So now notice we can go ahead and factor the 2 here. So 2 times 2, that'll be a 4 pi over 3 r squared minus lowercase r squared to the 1/2. And then now, of course, we're left with r squared minus r squared with the cases that we know. But that's just the first power. So to kind of make it look real, I'll just put a 1 there. So you're thinking that's the same radicand as that, so we can put them together. So now we get 4 pi over 3. And now we have uppercase r squared minus lowercase r squared. 1 plus 1/2 gives us a 3/2. So now the thing about this is that this is not a problem that you do in high school. I mean, you don't have a day where your teacher says, okay, here's the volume of a ring. Okay, so this is a new result. The technique is new, and of course the formula is new. And as future engineers or future STEM professionals, you see now that even if you have great software systems to do work and all, you still have the setting of the stage, so to speak, the hypotheses, setting up the problem, and you can use your nice software. Many engineers have tons of elegant software that they use to make models and to make drafts and things. I mean, that's really revolutionized the profession. But unfortunately, the math and the physics haven't changed, and that's the same. So everything engineers had to learn 50, 60 years ago, you're still having to do the same thing. You just have some fancy gadgets that they didn't have. So the math and the physics still the same. Now, the idea, again, as you work these problems, use the more complicated derivations to kind of ground you. That once we decide that we have a formula, then now we get buried in the algebra of pushing it through, just like the integrals you did with the inverse trig function. Sometimes you have to make adjustments to make them work out. Now, what I want to do is to provide a little intuition about the shell method. And I want you to go ahead and read about the cross-section method. I think you can figure that out on your own. And I'll make a little short video doing a couple of problems with that so you can complete your homework. But this information is extremely important. Now, I have here this is from your lecture notes, and I want to say a little bit about it. When we do a shell method, we actually are thinking of, instead of creating washers or discs, this is right from your scanned in lecture notes. And I just wanted to say something about this. Very simple, but instead of creating a washer or a circular disc, we're going to create a cylindrical shell. So what Dr. Larson does, and again, the Riemann sum thing is like we've done before. That's really something you've seen. So what we've noticed when we've applied the disc method and the washer method is that we take a rectangle that is perpendicular to the axis of revolution. So you're thinking, we're fine with that. Why do we need another method? Okay, well, the idea is that mathematically, the shell method is very nice. And what it happens is that there might be instances where the shell method may be simpler. There may be instances where you try the shell method, like you see in your notes, where the shell method is exceedingly difficult and the disc method is easier. Or there might be a situation where one method provides an integral that you don't know how to compute, but the other method provides an integral that you understand. So as a physicist, as a science student, you may find that, okay, I'm using this method because I can actually do the integral. So what we do with the shell method is we first just figure out how do we find the volume of a cylindrical shell. So we think of taking a strip that is parallel to an axis of revolution. So the notation is what Dr. Larson uses, and I will continue to use that, even though you might think, why doesn't he just call that an L? Well, he calls it H for height, so you can think of it being horizontal, so to speak. So you take a strip or rectangle of length H, and we have P to be the average radius, that is right in the midpoint there. And we have the strip of width omega. So this is kind of setting up for infinitesimals when we do the Riemann sum. And so you're thinking, I know the volume of a cylinder, that's pi r squared h. So that's something I learned in high school geometry, and I could use the disc method to prove that. So what his derivation provides is that you actually take the difference between two cylinder volumes. So when we look at this, we're thinking like we're doing a disc method. We have an outer radius of P plus omega over 2, which is the distance from here to that point, which I've noted here. And then we have an inner radius, which is a distance from the axis of revolution to that point, which is P minus rho over 2. So this is basic. I could teach my college algebra students to do this because they know the volume of a cylinder. They learned that in high school geometry. Now, to get the volume of the shell, we take the volume of the outer cylinder and subtract the volume of the inner cylinder. So again, this is pi r squared h minus pi r squared h. Now at this point, we just do some simple algebra. And I thought you might like this because this is actually very simple. One thing I like about Dr. Larson's text, it is the most mathematically elegant one that exists. He is actually a topologist. He is truly a mathematician. And his book is flexible. Engineers love it, math majors love it, physicists love it. It is a remarkable textbook. Now, of course, no textbook is perfect, but I have found it to be one of the best sources of information for my students. And after 11 years at San Jac and tons of graduated engineers and math majors and physicists, I know it works. So now let's go ahead and square all of this out. Notice the pi and the h are common factors in both of these expressions. So very simple. Now let's expand the binomial. So we get p squared, and then of course we get p times omega over 2 times 2, which gives us p omega, and then square omega over 2, which gives us omega over 2 divided by 4. Again, the identity, what are we using? The perfect square, the binomial. Now here we've got the minus, so we put the minus here and go ahead and expand this. So again, we get the p squared, and then we get the p times the negative omega over 2 times 2, which gives us negative p omega. And then of course, as we square it here, we get omega squared over 4. So very simple algebra here. I do these kinds of calculations with my pre-cal kids to get them to remember these identities. And now what we want to do is go ahead and distribute this negative. These first three terms we just moved down. So here we get a negative p squared, negative negative, positive p omega, and then negative here, negative omega squared. Now notice, when you look at these, absorb, these absorb. So what you can do, let's just go ahead and put boxes around them. Absorb. And now if we see the p squares absorb. And all that remains are 2 copies of p omega. So we have 2 p omega times pi h, or 2 pi p h omega. So now you're thinking, well, isn't this interesting? When we do the shell method, instead of a factor of pi, we get a factor of 2 pi. So when I was doing the symmetry in the previous problems, we had a 2 pi, but it was a 2 times a pi due to the symmetry. It was still the disk method. So what we have is the 2 pi. We have the distance to the axis of revolution, the length of the strip, and the width of the strip. So now, this I do want you to know, this little simple derivation. I would like you to know that this is easy. Has everybody had opportunity to write this? Have you gotten this down to this point? That's all I need for you. Everybody okay with that? Okay, now, when we actually do the formulas, we just move this into a formula right here. So we can use an independent variable, x or y. So now when we compare here, we have the 2 pi. We integrate from a to b, distance to the axis of revolution, length of the strip or height, omega is replaced by dx. So now what we can see in this particular case is that the formulas look very different. For instance, when we do the washer method or the, let's see here, okay. Let me get rid of this. Now what we see is when we use the shell method, like I said before, very, very different. 2 pi, distance to the axis of revolution, length of the strip, the width of the strip. So again, we don't see the geometry of the area of a circle like we see with the disk method and the washer method. This derivation depends on the difference between 2 cylinder volumes. And so now when we look at this, they look kind of strange. But the idea here is that, again, this offers a different approach to computing the volume of a solid of revolution. So let me say this, I will say this several times. If you are asked to compute the volume of a solid of revolution, you compute it however you want. If I request, or if the problem requests that you use a particular method, then it's probably best to use that method. However, if you use the different method or the alternative method and you do it correctly, I don't really care. I do, however, want you to be able to use this method. I live by the philosophy that a correct method is a good method. I'm not going to be offended. I don't get offended if you do good mathematics. I do, however, want you to be able to use this method, and there'll be cases in the lecture today where we'll use it. So I want you to have familiarity with it. But it's kind of like solving an equation in any course. However you solve it is up to you. You use correct mathematics, and that's fine. So if I'm looking for a particular technique that I'm actually testing, then I'll say, please use this method. But otherwise, you are free to use whichever method is most convenient to you. So now let's do an example of this. So we want to practice with the shell method. So here's an example. So what I'm going to do here is, just to remind you, is use shell method. In the notes, I worked out a problem with the shell method. Then, and my comment at the bottom of it was, you see how long and arduous this was. So it's often good to use a method that is easier. We don't want to be in a situation where we feel like that we were bound to this method and we had to use it. So now here's the particular region. So again, revolve, here's what we're directed to do. Revolve the region about the x-axis. And here's our region. Again, we will define it, y equals 0, the x-axis, x equals 0. I kind of changed this up a little bit from the WebAssign because they gave you a picture. They didn't give you the actual curves the way I like to do it. So I changed it a little bit. And y equals the square root of 16 minus x. Okay, so again, we want to use the shell method because we want to get some practice with it. So again, you can see that this is going to live in the first quadrant. That's a positive square root function. We've done a little bit of work with it. That is, we've got it opening to the left, and it's moved over. So this is where we're actually using some college algebra transformations. So let me just remind you of that. We start out with the square root. And to make this actually work in a way that will be good, we can do this. We can say, okay, let's do a right shift by 16. Right shift, I'm just doing this off the cuff like I do most things, because we always need the opportunity to remind ourselves of where we've been. And now let's do a reflection. Y-axis reflection. So this will be, we just take the negative of what's on the inside. and that equals this. So that's just a college algebra problem. So now let's just draw a little picture of this. So we can just use this idea. So we got a 16, we get a 0. And then, of course, when we put x equal to 0, we get the square root of 16, which is 4. So my scale's a little bit untoward, but keeping it simple. So I can draw my square root function. Right there. That's the vertical tangent. You know, right there we have the vertical tangent. You always want to try to make that a vertical tangent. Now, the idea here is we want to do this. Now, again, you don't have to do this, but it does help to orient things. Now, just like I said before, when we do the shell method, we pick a y, in this case, because the shell, the rectangle must be parallel to the axis of revolution. So let's just draw it. So we have to do a little bit of algebra here. Now, like I said before, remember back in college algebra, when you apply these transformations, you apply it to the entire function or the entire argument. Many students forget that when you have more than just an x, you must apply it to the entire argument. So you have to distribute. So be careful to remember that. These are important topics, and lots of times I'll have students tutor their friends and they get it wrong. So be careful. Now what we can see is the distance here to the axis of revolution is just given by y. So we've got y between 0 and 4. And if you like, go ahead and do a little shading here. So here we have p of y is just y. Okay, so that's simple. I think the elegance of the shell method is really neat. And now we need the length of the strip in terms of y, but we don't have that. Now this is what the WebAssign problem was doing. They gave you the function turned around, but what they drew was not that function. It was the entire quadratic. And so I thought, this is no good. This needs to be written this way just to give the students, well, it makes you work harder, but it's more correct. So now let's just go ahead and square out everything. Y squared equals 16 minus x. And now let's do the transpose. So x is equal to 16 minus y squared. So now this will give us the input. So now we input the y and out comes the x. So now we have the height of the strip or the length of the strip is 16 minus y squared. So that's where we have to do a little due diligence. So when you do these problems, ladies and gentlemen, whatever your independent variable is, that must be respected. But notice in many cases, the distance to the axis of revolution will just be the independent variable, and that's easy. Okay, so now, so what's important here, and you know I say things over and over, but just remember with the shell method, what's the key? Parallel to the axis of revolution. Parallel. Okay, so now the volume of the solid, I have to admit that these problems are fun because they utilize so many aspects of what you're going to be doing in the future. So remember, we have the 2 pi. 2 pi is part of the formula, no symmetry. So right here, just say formula. Now, if I said on a quiz, or on a test, I'll say the formula for the shell method is a definition. Would you say true or false? What would you say? True or false? Anybody? Everybody shy this morning? Well, I'll be the student. Professor Ron, is true. Yes, because you motivate the definition through algebra and calculus, and you define it to be a particular formula. It's not a theorem, okay? And now, our limits of integration, 0 to 4, and we want to fill in. We want the distance to the axis of revolution, y. So this is the P of y. And then the length of the strip. We like these simple integrals. So just call this the H of y. So you can see that this method, when it works, is, it gives you a reasonable, and then of course the width of the strip, dy. So you can put the delta y there if you like. So now what we're seeing is if you start to do a problem and it doesn't require you to use either method, and you get an integral that's really kind of frustrating looking, you can try the other method. Maybe it is an improvement. So you always have that option. So now, of course, we can make this table ready because we've got that -2y in here. So we can use I think I've written this up in your notes. A lot of these you'll find written up in the notes because they're standard problems that are very, very good. And I don't want to leave out a problem that I know is good. So now we have 16 minus y squared, and I'll just put to the 1 power. And then of course we need the -2y dy. So I'll say -2y dy. So of course, with the differential, we have to pay for that out here. So we have to divide by a -2. So the idea is that now we have table ready if we just adjust the differential here. So again, we have u, we have du, we're good to go. So the reason I like this is because this is just add 1, divide by the new power. So and of course, that'll be a -pi. So the new power is 2, and division by 2 is 1/2. So we get 16 minus y squared, 0 to 4. Okay, so again, very simple integrals. I guess you could multiply that out, you'd get the same answer, but when it's simple to do the u du, that's always a plus, and that bails us out of really icky situations at times when we're looking to utilize these methods. So now we've got a -pi/2. And note, when we substitute the 4 here, it's not a 0, we get the 16 minus the 16. So this annihilates. So we just get 0 squared there. And we have minus. And now, of course, when we replace with the 0, we get 16 squared. So let me just write this out. That way you can see it. 16 minus 16 squared, and that's 0. Okay. So now we get a -pi/2 times a -16 times 16. All right. So now the negatives absorb, we get pi/2. So I can write that 16 as 2 times 8, right? And then times the 16. So this is the symbolic calculation I teach my pre-cal students. The 2's absorbed, and then I've got a pi here. And then a 4 times the 6, that's an 8. And then carry your 4, that's a 128. So we get 128 pi. So the key with a lot of these problems is that it may not matter which formulation you use. That is, maybe you do use the disk method, or maybe a colleague uses the shell method, and both integrals turn out to be readily doable. So there's probably not a good reason to use one or the other. But what we'll find is that when we're doing certain formula derivations and all, that it might be the case that one is clearly easier because, number one, we get integrals that we can do, or we get integrals that utilize our knowledge that we can push forward. So maybe we're using some properties from Calculus 1, maybe we're using some geometric properties. All of these things make doing the integral easy. And since integration in general is much more difficult than the other processes we've learned, we want to take advantage of everything that's out there. Now, let's look at another example. Now, what I have here is just a simple example that we find that the shell method is very useful. So here's another example, and then we'll do a volume of a torus. Now, when you get to calculus 3, you'll actually parameterize a torus. That's kind of a formidable task, and you'll be able to do some calculations with it. As we move into calculus 3, we'll do at the end of this class some parametric equations and parametric representations of curves, and then you'll segue that into Cal 3 when you get to chapter 12 in Dr. Larson's book. And it's some nice material you future engineers and physicists will enjoy. Now, again, I want you to use the shell method. Now, here's the region. So here's what the WebAssign says. It says revolve region. I say the WebAssign. WebAssign's become, a proper noun these days. It's become very popular. WebAssign was invented at North Carolina State University, my home state. My undergraduate career was at the University of North Carolina, Chapel Hill. And so they were our arch rivals, though at the time I didn't really care. But they did a lot of work with software engineering. And then Cengage actually bought WebAssign from North Carolina State. So now Cengage owns the WebAssign. So that was an interesting tidbit there. So revolve region about the y-axis. And here's our particular region. We have y equals 6 divided by x squared. We have y equals 0. Lots of times the curves will be relatively straightforward where you can use your trig or your college algebra techniques. And those transformations are very powerful. Transformations of functions are nice. When you got to Cal 1, you don't worry about using calculus on functions that you can already graph. I mean, that's a waste of time. So the transformations are very much time savers. Now, when we look at this, we think, okay, we've got a reciprocal function here. And then, of course, we've got the first quadrant moving through here. So let's just go ahead and look and see what we get with this. This is a simple rendering. And again, when you do the areas, maybe the sketch of the region is not really that important. But when you're using a new method for solids of revolution, it does help to get some kind of idea as to the orientation of the strip and how it works relative to the region. So I would recommend that. Now, of course, we have x equal 1. We'll just spread this out because we can do that. X equal 1, and then x equal 3. Again, you don't have to worry about your picture being perfect. You just want points in relative positions, just like you did in Calculus 1 and Pre-Cal. So now, and of course, we have y equals 0. And now, of course, when we have 1 here, we get a 6. So I'll spread this out. So we get 6 there. And this is a nice decreasing function. And then, of course, when x is equal to 3, we get 6 over 9, which is what, 2/3. So I'll kind of cheat a little bit and say that's 2/3 so we can see it. So we'll go down to here. Again, just so long as we've got relative positioning of points. And now we can draw in the curve. We know it's decreasing, so we'll just kind of think that like this. So this is becoming asymptotic to the x-axis. So that's more than sufficient. Just kind of draw it, make it look somewhat professional, as they say. So now what we see here, take your red pen and do this. Well, let me turn a little bit for my email. When we had training during in-service, they said, turn your email off, but I have to know that, you know, just in case I'm doing conference hours, if someone misses the link and things of that nature. So now notice here that we have the vertical lines, we have the x-axis, and so when we look at this, we have this region here. Again, just to get a little picture of what's going on. And now, since we're revolving about the y-axis, we want to take the rectangle parallel to that. So now we can say, all right, let x live, and of course these are easy. We don't have to work hard. We already have the limits of integration. Like I said before, usually when you're given vertical lines or horizontal lines, that makes the work very easy. So we can pick an x here and then just draw the rectangle. So again, we have a delta x in this case. Now, like I said before, this often relies upon the independent variable to give us the distance to the axis of revolution. So here, we see that p of x is just x. So again, with the shell method, we always need the distance of the strip to the axis of revolution. That's the biggest difference with this method. And now, the height of the strip or the length of the strip is just given by the function. So we didn't have to work as hard with this one, no algebra adjustment. So this, we can just write this as 6 over x squared. Okay, so again, we can sometimes see that choosing one method over the other creates a very simple situation, and this is that way. So now we'll have the volume will be 2 pi. Remember, this is part of the formula. You will forget this. You'll remember the pi, but you'll forget the 2. Or you'll be doing symmetry with the disk method and you'll forget the 2, or you'll forget something. It's okay. It's just remember, you must take your time. Take your time working through these problems. Take your time working through the homework, doing consistent work, reminding yourself of what you need to do. Because WebAssign will not give you any slack. If you've left it out, then the response is incorrect. And so you ask my Cal 3 students from the summer who got frustrated because, again, you have to set each part up with intention and work through and double check it. Let the math correct you, because it certainly will. So now we have limits of integration, 1 to 3. And we need our p of x, distance to the axis of revolution, which is x. And then the length of the strip, 6 over x squared. dx. So now, very simple, back to Cal 1 integrals. We can factor the 6, so that gives us a 12 pi, 1 to 3. And then, of course, the x divided by x squared is dx over x. So we're like, okay, fine. We like these integrals because that's our friend, the natural log. Again, another jewel from Calculus 1. Without Calculus 1, we don't do this class. It is imperative that we know our Calculus 1. So remember, du over u. That is one of the basic forms, natural log of the absolute value of u plus a constant. And again, we see that this filled in the gap from the power rule. So we had to find something. I mean, students are always frustrated. It's like once we get to this point where we can fill in that gap, they feel better. So now we have 12 pi, and we have the natural log of the absolute value of x from 1 to 3. So this gives us 12 pi, natural log of 3. We don't need the absolute value. And of course, in the WebAssign, they always like you to use parentheses. Here we don't need it. But if they put in a parenthesis, you close it. You know how the routine works. A natural log of 1. And of course, the natural log of 1 is 0. So we have 12 pi times the natural log of 3. Now, again, we can see that when we're learning a new method, we want to use it. And again, you will always have the option of choosing one method over another. So again, if you're finding the volume of a solid of revolution, you are not bound by any method. There will be, I mean, if you're doing a quiz, it says use a particular method, that's okay. You use whichever method you want. Maybe the quiz is giving you a hint. Maybe they're saying, please use the shell method because you're going to get an integral that you can't do with the disk method. But like I say, there's not going to be any type of edict that says you have to use any particular method. If I give you a test and I would like to see a particular method, that's fine. But if you're doing something on the WebAssign with a quiz, then you are free to use whichever method you like. Now, I want to look at another formulation that we have. Even though we're not actually generating a formula, we're setting it up kind of like the initial problems with the disk method. And I wanted to do a couple of review items, because often when you get into Cal 2, you may have talked about these things, but they may have become rusty. So for instance, let's just write down these are theorems, 2 important facts. So first, I'm going to say, suppose f is continuous. Again, I'm just going to assume that it's continuous, so we have a Riemann integral. Suppose f is continuous on the interval -a to a. That is where a is some positive constant. So remember, we call this a symmetric interval about 0, a symmetric interval. Suppose, and we need a, what is it when you talk about even and odd? Oops. I don't need to break this. Here, let me fix the, oh, here we go. Start moving my hands to make a gesture, and then I'm glad I've got this document cam was rather pricey, so it can put up with Professor Ron and his antics. So I'll do this again. I'm used to teaching in a classroom where I can make gestures and things, and obviously I can't do that here. But when you do your even and odd functions, you have to have a symmetric interval. You have to have a full complement of the interval. So when I talk about even and odd, I must have a symmetric interval. The real line, that's symmetric about zero, right? You know, or you can have an interval that is symmetric that has certain symmetric numbers deleted, like maybe -2 and 2 are deleted. As long as you have the full complement of the interval, then you're fine. Now, suppose f is odd for x in this interval. So we have an odd function. There we go. Then, and this is the result, the integral from -a to a of f of x dx, what do we know that to be? Do we know this? Anybody? Do we know this integral? I mean, do we know this integral from a theorem? Anybody? Everybody is shy. Okay. So nobody remembers this from Calculus 1. You should have taken Professor Ron for Calculus 1. That's okay. It's zero. The integral of an odd function on a symmetric interval is zero. And you should have seen that in Calculus 1. That is a major theorem that, of course, in Dr. Larson's book, even as an undergraduate at Carolina, we did this. So this result, it's kind of like using the geometry of the situation to do an integral. Like if you're doing you've got a Pythagorean integral and it just turns out to be the area of a square, of a circle or a semicircle, then you can use that without having to do some elaborate computation. Okay, so if you've seen this before, good. If you haven't, no, you know now. And I would encourage you to try to prove this just using basic properties of the Riemann integral. Again, this is all Calculus 1, and we need to know this. The second item is this. Suppose f is continuous. And we also know, if you want to think in terms of a picture, an odd function is symmetric with respect to the origin. So you can see that you have a absorption, so to speak, of a positive area and a negative area. So that's one way to think about the proof. So f is continuous on the symmetric interval where a is positive. Now suppose, let's do the other type of function. Suppose f is even for x in the symmetric interval. Then, now we don't get zero, but we remember that the even function is symmetric with respect to the y-axis, so we can use the symmetry option that I've used many times already in this course. So this is the symmetry option that we use because we're trying to do less work. And I've been using this, but it didn't really require anything but looking at the sketch. We were using even functions, but I wasn't approaching it that way. So this will be 2 symmetry. Now the lower limit becomes 0 to a f of x dx. So that's a symmetry consideration that we've already been using. So I think you're probably pretty comfortable with this, at least though I did not refer to this result. This you probably feel better about. But this one is extremely, extremely useful. You do not want to avoid this. It's easy to figure out when a function is odd. And if you have a symmetric interval, then you are done. So this is a huge time saver. Now, of course, most functions are neither of these. These are very restricted class of functions. even and odd, there's a lot that has to be going on for that to be in place. So this is not something that you're going to see all of the time, but when it does arise, it can save you much time. Like I wrote here, huge time saver. So let's apply this result. So here's an example from your WebAssign, and this is also written up in your notes. What I do with you've got PowerPoints for this class, which summarize everything from the textbook. You've got your textbook, your ebook, and plus you have handwritten notes in addition to this. So I think it's overkill. So you have plenty of resources to use. And like I say, the more the better. The more resources you have, the more you can work with things and recast your understanding of particular techniques. So now what we want to do is compute the volume of a torus. Now, that's a word you may not have used before. The torus is the inner tube shape, the donut shape. Okay, now, we're not going to do this in general. The torus actually has an inner and an outer radius. And when you parameterize a torus, again, that's a big trigonometric exercise that is non-trivial. But we will get to that in Calculus 3. So what we're going to do is use the shell method, and we're going to do this. That is shell method, because this will give us integrals that we can actually do. Shell method here. And what we will do is we will revolve. So you're thinking if this is the inner tube, we need to revolve a circle, because the circle will create the torus or the donut. So revolve, in this case, the region bounded by, and we'll take the unit circle, x squared. So this is specific to a particular torus. So this is not the general version, but we've got to start somewhere. Bounded by the unit circle about the line x equal 2. And I'll just say about the axis, since I like to use that word, x equal 2. Because we always have the axis of revolution. That's important. You change the axis, you get a different answer. So the idea here is that this is almost like thinking about the volume of a ring, okay? We found that the disk method turned out to be very reasonable. It gave us reasonable integrals, lots of notation, but very doable. So now let's get a picture of this. We'll make it a little bit larger, just to spread it out a little bit. So go ahead and draw your unit circle. So there's our unit circle. Of course, this is 1, this is 1. Here's our x-axis and our y-axis. And now we'll draw in the vertical line, x equal 2. Now, one thing that I've noticed, again, that makes the problem doable and in a way that we can actually do this without having such a complication is to, again, use some symmetry. So, and I want you to think about this. We could go ahead and revolve the whole circle, but we can see that relative to the x-axis, well, it's symmetric all over the place, but relative to the x-axis, we have symmetry. So here's what I propose to do. I'm going to shade the upper portion of the unit circle, the region bounded right here, okay? This is very important. You must think about this. Now, if I revolve the upper portion, that will produce the same volume as the lower portion. This portion, not this part, this portion. And so I can use symmetry, I can double the result, okay? So again, what we're gonna do is use symmetry. This is only to make the calculation easier, but you can't use symmetry and not remember the factor of 2. So I'm just going to write here factor of 2. So again, if we revolve this portion, that will give us the same volume as revolving the lower portion to make the problem easier. Now, good to go. We see here, let's just go ahead and write, this will imply that we want the upper arc, but we've got y equals plus or minus, this is our friend from the very first problem, 1 minus x squared. So we will select the positive radical. Algebra and trigonometry and calculus, you really do have to watch what you're doing. It will burn you if you don't. So now, if we're thinking about this, oh, okay, got a -1 here. Oh, I see, Professor Ron, we have a symmetric interval. Interesting. Maybe we're going to use one of those results. So let x live between -1 and 1. Again, symmetric. And so now what we can do is pick an x and draw the rectangle. So now we're thinking, okay, this is not so bad. We can do this. Now, this is where we have to think a little bit and be a little bit more vigilant. Now, notice I'll do the easy part first. The length of the strip is just the value of the function at x. That's the easy part. So the square root of 1 minus x squared. Nice thing about calculus is just like doing anything. Once you get warmed up, you're in the flow. The toughest part about any test is doing the first problem. Once you build through the first problem, then you're fine. But that's the tragedy of having to test. Doing anything is that way. Now, we need the distance here. But again, we think about this distance here. So this is 2 minus x. So if we subtract x from 2, we get this actual distance algebraically. So this says that the distance to the axis of revolution is 2 minus x. All right? So like I said before, there's a certain amount of algebra due diligence that has to be done first, and then we can move to the problem proper. So we have everything that we need. We've got the symmetry here, so we're going to need the factor of 2, and we have the symmetric interval of integration, so we're being hopeful that we're going to be able to use that. So now, this implies that the volume, now first I'm going to use my 2 here. Put the 2 in the different color and just say symmetry. I've always thought, how can I emulate the whiteboard? And it's the document cam with the pen. So there's always a way to bring the classroom into virtual, and I think this is good, especially for a calculus class. And now we have the 2 pi, which is definition. Okay, that's awkward right now. It's very odd. 2 pi. Remember, this is from the derivation of the volume of the shell. The 2 pi just comes along for the ride because we get the 2p in the formula, and the 2 pulls out to join the pi. And then we have -1 to 1. Then we can write in our distance to the axis of revolution, 2 minus x, and then our radical. All right. So what, you know, in the more general setting, surface area and all of a torus is a little bit more complicated. It requires some techniques from Calculus 3 and of course a parameterization. But at least for now, what we do in Calculus 2 is we use everything that we know to do as much as we can. And then we formalize things when we get to Calculus 3. And then you look back and say, oh, we were doing that before. Now this is a more general setting. So now let's go ahead and work this out. We have a 4 pi here. And what we want to do is go ahead and distribute here. So we have a 2. And of course, we're going to get to use some geometry too. I didn't talk about that. I think you're going to appreciate that too. So we get 2 times the radical minus x times the radical 1 minus x squared. All right. Now we'll use linearity. We'll break this up into 2 pieces. So the first piece, we have the 2. So that's going to give us an 8 pi. So you're thinking, oh man, Professor Ron, we haven't done this, but we took Calculus 1. So good for us. So what we're finding is that at least with the shell method, it appears that we're going to be able to do the integrals that come up. And then of course we have the 4 pi, so we have minus, just distribute, good old college algebra, or really algebra 2, -1 to 1, x square root 1 minus x squared dx. Now, this is where we do our due diligence. So you look at both of these and you're like, what do I do? Okay. Note symmetric interval, and I want you to do a little sidebar over here, sidebar. So we're just going to look at this function right here. F of x equal x times the square root of 1 minus x squared. And we ask the question, is this odd? Well, it is. So if you were in a college algebra class or a pre-cal class and this were on the test, how would you prove it? Well, first, the definition, the domain of definition is obviously this. I mean, that's given in the problem. That's the domain of definition. So if you had to compute the domain of this problem or this function, you would get that. And then again, that would be a source of error for most students because they don't want to abide by the radical. And then what's the second step? Well, you check f of the additive inverse of x. So again, we have the additive inverse of x times the square root of 1 minus the additive inverse of x squared. So this gives us the additive inverse of x. And then of course, squaring the additive inverse gives us just the x squared. So we have 1 minus x squared. But by definition, this is just the negative of the original function. So we say f is odd. Now, of course, you don't have to do this computation when you're looking at this if you can just kind of say, okay, well, yeah, if I replace x with its additive inverse, I do get a function that is symmetric with respect to the origin. So again, thinking of the picture or just thinking of it algebraically, this is an odd function. So we have an odd function integrated on a symmetric interval. So just right here, odd function. So by the theorem, we know that that integral is identically zero. So we're done with that. Now we need another sidebar here. This is a Pythagorean integral. This is not the inverse sign, even though it involves the inverse sign. It requires a substitution, which we're going to learn about later. But if you see this integral, if you see this definite integral in a problem, you don't do anything but what I'm going to remind you of right now. Notice this is just this area right here. That is, note, -1 to 1 square root 1 minus x squared dx equals area of the semicircle. Semicircle x squared plus y squared equal 1. And what's the area of the unit circle? It's pi, so this is 1/2 pi. So you don't have to do this problem anyway but this. That is, when you take Calculus 1, lots of examples will say use the geometry of the integrand to compute the integral. And you're thinking, wow, okay, but like I say, you remove the limits and then you need an antiderivative, which will require substitution. So then that wouldn't be anything you could use. So the definite integral is a plus here. So now we get 8 pi. Let's fill everything in. Again, this is, I'll write this down, area of semicircle. And so we get 1/2 pi. And here we have 4 pi, and this is an odd function on a symmetric interval, and that's just 0. So now we get 1/2 times 8, which is 4, and pi times pi, or 4 pi squared. So what we see in this problem is a very, very efficient use of the shell method. That is, depending on the type of problem that you're trying to do, say you're working in an engineering problem or physics problem and you're doing a solid of revolution, you need to compute a volume. You would have to do some experimenting and say, okay, let me try this method from Cal 2, let me try this method. These are kind of like the methods you learn in college algebra. They're universal, they always work. But the only difficult part about doing mathematics and physics and engineering is what is the resulting integral? Integrals are difficult. They are tabulated, tabulated, and tabulated. The CRC handbook back when I was a kid were the integral tables that everyone used. Now you just go online and you can find software to do integrals. That they don't make you very smart. But again, the idea here is whatever type of integral that ensues really determines what method you're going to use. So we found that when we use the shell method here, we actually get integrals that we can do. So the reason I wanted to do this was to impress upon you that even though it looks somewhat hopeless right here, when you get to this point, you can recognize some nice properties. That is, again, odd function on a symmetric interval. A geometric property, that is the area of a semicircle. So again, you have to realize that you will see these types of integrals. Physicists really live by this. They use these properties all the time. I can remember as an undergraduate taking an electricity and magnetism course as a junior, and we used this all the time. We used a tiny little book that I still have that's falling apart. And it would just assume we knew all of these. And so it did make us better, but it was a little bit painful. Okay, so the good example, again, I think this is written up in the lecture notes, but again, you should write this problem down a couple of times and teach it to someone so you have it mastered. So again, the shell method is turning out to be a popular method. Now I've got another example here that I want to do, and then I want to say a little bit about another topic that we're going to be doing. I want you to get as comfortable with these types of integrals so that when we get to chapter 8, we won't feel like we've just left everything behind. Now, here's another example that a lot of you will see in engineering, and some of you will be taking probability courses. So I thought this would be a good example to utilize with the shell method. So shell method. So now we've got the following. That is, in this particular case, we want to revolve the region about, in this case, let's see, the y-axis. And here's the region. It's defined by y. So these are probability functions. Looks like the normal distribution. Yep. Theoretical probability and statistics, that will challenge you. That's real analysis. That is some good stuff, but it will challenge you. So we have e to the negative x squared over 3. Now, again, let's see here. Let me check this and see what. Oh yeah, let me make sure I've written this well. That's poor. I got a little bit sloppy with my notation. Yeah, this is a negative x to the 2/3 power. I wrote the 3 a little bit too large. That's negative 2/3. Yes. Just want to make sure I've let's see. Let me just check one thing to make sure I've written this correctly. So we have oh, I was correct the first time. So this is a probability. Let me just write it so it's clear. I don't need to angle things so much. So yeah, we go. Yeah, that's clear. The power is negative x squared divided by 3. So make that note. I was sloppy the way I wrote this, and that's no good. We don't need to be sloppy when we do our math. So y equals 1 over the square root of 2 pi e to the negative x squared divided by 3. The y equals 0, or x-axis, and the y-axis, x equals 0, and x equal 1. So this is a nice decreasing function, okay? So this is a decreasing function, like e to the negative x squared decreasing, but this is e to the negative x squared divided by 3. So the power of the exponential base is negative x squared divided by 3, okay? So that's important. Now, again, we want to revolve about the x-axis. So let's get a real simple picture of this and use the shell method. What I liked about this is the integral calculations. It's a good review. We haven't done much work with exponentials, so I wanted to throw this in. So now, notice, let's go ahead and spread this out a little bit. We'll put our 1 here. X equal 1. So now if we consider 0 here, we get what? Okay, so this becomes e to the 0, which by definition is 1. So we get 1 over the square root of 2 pi. So I'll spread this out, you know, to make it easy to see. So this gives us 1 over the square root of 2 pi right there. And then at 1, we get 1 over the square root of 2 pi e to the negative 1/3. So that's going to be lower. So I'll just approximate it here. So we get, at this point, 1 over the, I'm just writing the ordinate here, 1 over square root of 2 pi e to the negative 1/3. Good. Again, the notation is really important. Now we have a decreasing function. So let's just go ahead and sketch that in. I don't need so much upper curvature there. So this is going to be asymptotic to the x-axis. So just a little bit of curve, and that's going to be going out this way. So that's a nice exponential function. And we want to revolve about the y-axis. So now, again, x lives, again, with the vertical lines, we always get a breather there between 0 and 1. So we pick an x and draw our rectangle. So now, again, this is going to be something that we can make table ready. So that's why it's important to have that right. So now here's the axis of revolution. And we have the distance to the axis of revolution, which is just the independent variable. That's always nice. And then the actual length of the strip, h of x, is just the value of the function at x. So we get 1 over the square root 2 pi e to the negative x squared divided by 3. So now again, this is a fairly standard setup, like the 6 over x squared problem, but it has the exponential in it. And we need to review this because this is an extremely important function. And I don't think we've done much calculus with this yet. So now this implies that the volume, now of course with the shell method, we have the factor 2 pi. And then of course we integrate from 0 to 1. And now we have the distance to the axis of revolution, which is x. And then we have, oh, we've got to remember our friend here. 1, I'll put a little dot there just for emphasis, 1 over the square root of 2 pi e to the negative x squared divided by 3. So I'll make sure that fraction bar looks right. So now when we look at this particular problem, we can make this table ready because this is e to the u. So let me just kind of remind you, u is negative x squared over 3. So du, in this case, will be negative 2/3 x dx. That's why it's important to have the fraction written correctly here. So we can rig this for table ready. We just need to include this and then reciprocate it to pay for it. So now I've got this factor here, which I can extract. This is a really nice calculation. There's one thing about writing math that it's kind of like doing anything that requires notation, music, whatever. It's a very rewarding process. So now I'm going to go ahead and I'm going to pay for that. We have a negative 3 over 2. Then the integral 0 to 1. I'm going to write my exponential term first, e to the negative x squared divided by 3, and now put in my differential here, negative 2/3 x dx. So the reason we could do this is because we already had the x and we can move the constants in and out. So we get the correct differential. So now this is e to the u du, and the integral of that is just e to the u. So we call this table ready. So again, our friend from Cal 1, I'll tell you, Cal 1 was the barn burner. E to the u du is just e to the u plus the arbitrary constant. Again, remember the definite integrals have no arbitrary constant. The indefinite integrals have the arbitrary constant. So that again, if I left out the one with the log function, the du over u, please go back and put that in, because there's no limits of integration. So now when we look at what we have here and we think about it, we can rewrite things so that it's a little bit more user friendly. So now notice, and what I did with this particular problem is think about this in an algebraic way. So first, let's just go ahead and write this, 2 pi square root 2 pi. And then we have the negative 3/2. And let's see here. Let me go ahead and do this first. Just reduce this. I thought I would cut out the steps. But this will just give us the square root of 2 pi. Just go ahead and write that. I thought, well, they won't like that, but go ahead and write that. Just here, a divided by a to the 1/2, negative 3/2. And now, of course, we'll use this. So this is e to the u. And evaluated from 0 to 1. Now, if you like, here's what I wanted to do. We'll do a negative 3 times the square root of 2 pi. And then just write here, we'll write this as the square root of 2 squared. So we can combine those two, bringing the 2 here, and then that we can put that under the radical. And now we'll replace x with the 1, so we get e to the negative 1 squared over 3, which is negative 1/3. Then minus, now we'll replace the x with the 0, and we just get e to the 0. So if you will, this will be a negative 3. Now, when we put this under the same umbrella, we get 2 pi, 2 squared. So we have e to the negative 1/3 minus 1. And now if you don't like all these negatives hanging out, you can flip things around. So just factor the negative here, and that'll absorb that. So we have 3. And now we can write this as the square root of pi. And then, of course, the 2 will absorb into the 2 squared and give us pi over 2. And then, of course, 1 minus e to the negative 1/3. Now, the reason, again, I did this problem is because what appeals to me with the WebAssign and this book is that, well, they're excellent. Mastery of this textbook will provide you with a foundation to do anything in STEM. My students who master calculus do anything they want. I have a student now working on a PhD in computer science, Jose Daniel Velasco. He started out in college algebra. I knew he was good because from the very first test, he left out the last page because he just didn't turn the page. And he made like an 88, And when he got his paper back, he says, "Oh, Professor Ron, I know how to do this. I just left this out." And then, of course, every test after that, he made 100. So he was telling the truth. But the idea here is when you do these types of problems, what you're seeing is just an allusion back to Calculus 1. And so when I saw this example and I thought, well, I go through the WebAssign and I look for extra problems to throw in the homework to give you extra practice. This is just good practice with the standard exponential integral. And then, of course, if you get to your WebAssign, I actually use my Google calculator here. And because WebAssign said approximate to 3 decimals, so this is 1.066. I want this, but if WebAssign says approximate, they will give you the number of decimals. Don't ever use a decimal in WebAssign unless they request it. If you do, it's wrong. I mean, right now, like I say, you must remember to answer the way it is directed. This is the preferred answer, but if you're in a physics lab or something where you need a nice approximation, good, you can use your table of exponential values, or the cheap, available to everybody, Google calculator, and this will give you a very nice approximation. So just remember, go ahead in your homework and look at the cross-section method. It's very straightforward, but I wanted to spend more time getting into the shell method and comparing it to the disk method because I think pedagogically that made more sense. So I think I'll add an extra video with a couple of examples of the cross-section method so you can practice with that. But this particular method and how it integrates with the method of the disk and the washer is very important. So again, let me just make this comment. When you are asked to do a problem, WebAssign, quizzes, whatever, you can choose any method you want. If you're asked to find the volume of a solid of revolution, you are not required to use any particular method. So I want you to know that now you have a choice in the matter. And when we think about it, what's really going on here? When we do this shell method, we're actually using Calculus 1. So at this point, this is just a lot of algebra, make it look nice. Again, and I like the fact that when I lecture, that I'm very sure to make my notation consistent, because when I write things down and I'll think, oh yeah, that's this. Then when you think about it and it's like, wait a minute, my students need to read this correctly. So normally here in probability calculations, this coefficient is different, but it's always the power of x squared, the negative x squared with some coefficient. So that's important. Otherwise, this nice little table ready part wouldn't work very well, okay? Now, and again, just to recap, when we go back and think about the problems that we've done, we've utilized a new method. So go back and look at your area calculations, your disk and washer, and now apply this, and now you'll see that they're all related, that doing one actually helps you with the other. And you see that as you work through these types of examples, you actually get much better at Calculus 1. Now, when we actually need a result like we had here, I want you to make note cards of this. You should have note cards of all the inverse integral formulas, inverse trig formulas that we've done. You need to make note cards of these. You need to make note cards of the methods that we have with the definitions, and practice writing them down, then do practice problems. You will not find good success in this course unless you study it consistently. I'm saying this because after teaching at San Jac and actually being a TA at Texas A&M, I actually taught math when I was an undergraduate at Carolina, and the students would always complain, you know, then I was Ronnie because I was just this tall, and they said, you give too much homework. I said, well, Dr. Falsgraf told me that I have to make you work, okay? So what I found is that with my background, the hard work always paid off. Now, everybody's different. So you form a study plan that helps you get to where you want to go. Always make sure that you are utilizing enough time each day to have security. And I'm very pleased with what I'm seeing. I think you're working very hard, but like I say, don't ever let up. You know, when you have fun, when you can say HAPPY, I'm happy, that's when you take a test and you've done well. Studying math, doing STEM, the process is not a lot of fun, but the reward comes when you do well, and then you can sit back and say, I'm happy. So just keep that in mind as you study. I appreciate your attendance today. Everybody have a good day, and I have office hours today, so if you have additional questions, please come by. See you later.
Thank you.
Thank you.
Have a great day.
Have a good
You
day.
too. Everybody study that math.